Swayam Prabha. Digital India. Educated India.
Okay. So in the last several classes, we were looking at a chemical master equation based approach to simulate a stochastic process that often involve diffusion like process or chemical kinetics. And we were mostly looking at some simple problems where we can solve analytically. And I think the last couple of classes we also discussed how to numerically integrate the master equation. So even in the absence of analytical solution, you should be able to simulate numerically and get the statistical quantities like mean and standard deviation and so on. Okay. So continuing in that direction, we can actually think about more such problems relevant for chemical engineering. And in these cases, what we can do is we can just set up the master equation and stop there. And from there onwards, instead of looking for an analytical solution, which becomes more and more complicated, in some cases you will find the analytical solution, but I think I would recommend that we use the chemical master equation and try to adapt numerical techniques to solve them. So here I have given some topics. As you can see, these are all chemical engineering relevant problems. For example, you have a gas molecule, a gas dissolved in an inert solvent, and then this molecule is going to, the gas is going to diffuse around, okay, and then if this reaches the boundary, the gas may evaporate. Okay, a very simple example is how CO2 is captured in Coke bottles, Coke drink. Okay, so now when you open the thing, you see that carbon dioxide comes out of this liquid. Okay, so chemical engineering problem, basically a desorption of a gas. Or we can also think about diffusion control reactions. So the chemical kinetics we have discussed before, they all were about well mixed batch system, okay, where there is no concentration gradient within. But in many cases, there is a reaction that is controlled by diffusion. So you will see a concentration gradient spatially, okay, and especially if you want to look at heterogeneous reactions, packed beds, you see this diffusion control reaction becoming more and more important. So we can also solve diffusion control reaction from the stochastic approach. We looked at diffusion separately, we looked at reaction separately, now we can combine them also. Nucleation is another important process that if you have a supersaturated vapor or if you have a supersaturated solution, it undergoes a phase transformation going from vapor to liquid or from liquid to solid. This is something that happens through nucleation and growth, and this nucleation can also be looked into kind of a stochastic process, and you can set up master equation. Bacterial growth from a fermentation point of view or bioprocess operations, bacteria growth is something very important, and we can also use chemical master equation to set up this problem. And then also reversible bimolecular reaction. So all the reaction kinetics we have looked at before had only one internal variable, the other variable was obtained based on some mass balance. But here if you have a bimolecular reaction, so how do we set up? Okay, so these are some very small set of examples, but the purpose of giving all these examples is that when you get familiar with these sort of examples, maybe for your project you can look at more detailed problems, more complex problems, and then you should be able to apply the techniques that we discussed in the class. Okay, so let's look at these problems one by one. So the first problem is something like, from an experimental point of view, you basically have a vessel containing a liquid, and then in this liquid you have some gas molecule dissolved. Okay, and this liquid is inert with regard to this gas molecule. So the gas molecule is going to diffuse in this background of the solvent, and then if it comes to the surface, this can also evaporate, like I was giving an example of CO2 absorbed in a liquid water. Okay, so here clearly, if you want to solve this problem deterministically, what you would do is you would write a diffusion equation doing it in one dimension, but you can do for 3 dimension also. So this is a diffusion equation. You will know what is the initial concentration, boundary condition, initial conditions can be set to solve this, and very important thing is about the interface, the boundary condition. So we want to say that at the boundary, suppose if I say so this is x equal to 0 and this is x equal to L. Okay, we can say that at L the flux, that is dou C by dou x at x is equal to L, should be equal to some mass transfer coefficient times area times C at L, something like this. Okay, so the diffusion at this boundary is going to be equal to the mass transfer rate due to evaporation, mass transfer coefficient times area times the concentration at L. Okay, so you have a governing equation, you have a boundary condition, you can also supply the initial condition. This is how you would solve this problem from a deterministic point of view, right? So now what we want to do is do the same problem, but more from a stochastic point of view, using a chemical mass equation. So the way you can set up this master equation is the spatial domain here is discretized. Okay, we think of a lattice point along the x direction. So you can say this is lattice point 0, 1, 2, 3, okay, and the particle, the gas molecule can jump from one to the other, like how a one-dimensional diffusion happens, one-dimensional random walk happens. I have a state which is called a dead state to mimic evaporation. If a molecule is at this boundary, so this site 0 here refers to the boundary, like here, okay. At this point, there is a rate at which it can be evaporated, okay, and this is a dead state, it's not going to come back, it's gone, okay. So for this, it's going to be a dead state. So then what we can do, for n 1, 2, 3 onwards, this is like a pure diffusion, okay. So for site 1, 2, 3 all the way up to, you know, semi-infinite, you know, how long, whatever length you want to go down, you basically write a single one-dimensional Brownian walk, that the state at n, if you look at you know, suppose state 2. So this state can be created by a random walk from 1 to 2 or a backward walk from 3 to 2, okay. These are creation of probabilities. Whereas while over your state 2, you can either jump to 1 or you can jump to 3, okay. So here I am giving an intuitive picture, but you can set up the full master equation, look at all the intermediate states, and then you can also substitute and find this. But or else you can draw this kind of a schematic and discuss what are the states that's going to create or destroy the state. For any nth state, there are two processes that creates them and there are two processes that destroys them, purely a diffusion, okay. So that's what we have written here, that a state n can be created by a random walk from n plus 1 state to n, that is this, and it can be destroyed, sorry, this should be plus. It can be also created by a random walk from n minus 1 to n, and then there are minus 2 p of n, because it can either jump there or it can jump here. So for n is equal to 1, 2 onwards, it's a pure random walk, one-dimensional random walk, no big deal. But then when you look at this site, this is a boundary site. So here we write a separate equation, because here this state, there is no state like here. We don't have a dead state, there is no recondensation, there is no condensation, so this is not there. And you have this state though, that there is a rate at which it is evaporating, but this evaporation rate is different from the diffusion rate. So we want to qualify this rate separately, differently, okay, because we want to associate some different evaporation rate. So that's why I am writing a separate equation for the boundary site, which is state 0. So here what happens is, if you look at this 0 state, it is created when there is a forward jump from state 1 to state 0, this creates, and then it can also jump back. This is just a pure diffusion. So P1 is creating, this is destroyed. Now while you are at this state, it can also evaporate one way, so that is C times P of 0. So this C here is a rate constant, okay. This is to represent the rate of evaporation. This must be related to the mass transfer coefficient K here. So one can go about and try to solve this analytically, but it's going to be taking a little bit more mathematically involved procedure. But what you could rather do is solve this numerically using an Euler method, okay. Discretize the time, and you have a fixed lattice points, and then you will solve. What you do, what you will get by solving them is that more like a concentration profile as a function of time, okay. So you can solve for n is equal to 1, 2, 3, 4 all the way up to whatever n you want, and then the boundary site, and then you can plot the probabilities of finding a molecule at those states. Essentially that gives you a concentration profile, right. So we have basically what we have done, we have the regular diffusion, and then we are just having a special boundary condition to mimic the evaporation, okay. Suppose if you have a condensation also, suppose if this process, you can actually have an additional term to describe the condensation rate also, and the condensation rate can be different from the evaporation rate. So you can have an additional term here, but here in this problem there is no recondensation. And here we have looked at one dimensional problem. If you want to do it in 2 dimension and 3 dimension, you can do the same thing by looking at nx, ny, nz or n1, n2, n3. to describe the spatial discretization in all the 3 dimensions. Okay, so that's something you can easily adapt. Yeah, are we clear? I will also give a reference. This problem is solved analytically in a very detailed manner. So, physical review A, volume 39, page 2112. This is here. So, this paper has analytical solution of this problem. Okay. Again, you have to apply generating functions, do some sort of a transformation and get the moments. But I thought that doing numerically is far more easier in this case. So, if you think about this reaction A plus B going to AB, so we are talking about the second example now, A plus B, so there are 2 molecules, okay, and usually in a batch system we can think of this as a well mixed system, so there is no spatial gradient. That is our usual way of doing it. In fact, I will come back to this problem at the last, but here we are talking about something special. We are talking about a case where A is diffusing and then it reacts to B, but B is non-diffusing. B is actually kept at a particular location. So, A has to diffuse and find B, then this reaction AB will happen, okay, and then you can also have this AB splitting into free molecules of A and free molecule of B, then this A can diffuse backwards, right. So, we are talking about a diffusion control reaction where one species is diffusing, other one is fixed in space. You can also let this also diffuse around if you want, but just to keep this example simple enough, we are keeping one fixed, one diffusing, okay. And again this can be done in a one dimensional formulations. So, we have so the spatial domain is discretized into a lattice here, one dimensional lattice. So, this is the boundary, okay. So, this is the boundary, this is the last, this is basically the interface. Molecule A can be anywhere here, okay, it is kind of diffusing. Once you have molecule A here, it can actually bind with molecule B. B is sitting here at this state, okay, just outside this interface. So, A has to diffuse all the way here. Once it is here, you can actually react with the B, okay, but this bound state AB can also diffuse back, can also dissociate back to give A, and this A can freely diffuse back, okay. So, that is the kind of, so very similar to this problem we talked about here, okay, but only thing is here we are saying that there is a forward reaction to form AB and there is a dissociation reaction to release this, okay. So, in this case we can write the master equation, again simple one dimensional random walk. So, So if you look at this equation is exactly the same as this one, okay, talking about a simple one dimensional random walk as well as we are in the bulk, okay. It talks about the forward, backward, unbiased jumps. However, we write separate equations at site 1 and site 0. For site 1, what happens is this term that you see here is basically a random walk jumping from state 2 to 1, okay, that gets created. Then this state can actually jump back, okay, and that is one of this minus sign, and then it can also jump here, and then you see this is one, that means that while there is an unbound state, it can actually dissociate at certain rate and create P1, okay. So this one account for dissociation from a bound state to this. This is not a random walk, this one is a random walk, going from 1 to 0 is a random walk, but this from a bound state to this is actually a dissociation rate. So that's why I have gamma times P naught, gamma is a dissociation rate. Whereas if I look at this this state, that's very clear, you have one random walk jumping from here to here, creating it, and then there is a dissociation backward, very simple, yeah, per unit time, it's a probability per unit time. So in all these cases, handling diffusion is easy, okay, one dimension or n dimension, but I think you have to be very careful about setting up these boundary equations by looking at what are the processes that are going to affect the state near the boundary, okay. So in the previous example, we created a dead state to model a evaporated molecule, not going to come back, but here on the other hand, this is not a dead state, it is still a kind of an active state where molecule can be formed and can be dissociated back, okay. So there is a small difference between this problem and the other problem. Also think about how you would model this problem deterministically. Again, you will set up diffusion equation all the way up to here, and then the boundary condition you would have to account for a reaction. So instead of a mass transfer rate here, you would have a reaction flux minus RAV, okay, KCA for forward, and then backward minus KB and so on. So okay, so again, this problem can be solved deterministically also. So nucleation is basically a cascade of an aggregation process, okay. So if you have a supersaturated vapor and when it condenses into a liquid, if you look at microscopically, what happens is that these monomers combine together, form a smaller aggregate, and this aggregates consumes more and more monomer and becomes a nuclei, and then the nuclei grows, okay. And there is a thermodynamics part of it, there is an activation free energy and that has to be overcome and all that. But then you can also simply look at this problem as a cascade of an aggregation state. Two monomer forming a dimer, like a bimolecular reaction, and this dimer can take one more monomer, become a trimer, and the trimer can take one more monomer, become a tetramer, and then it goes all the way, okay. So these are all happening parallelly, okay, and there is a rate constant for all of this, and in fact it can also be that it can also reversible, this can be reversible also. A cluster can also dissociate and then form again, okay. It's a very dynamically reversible process. So here what we can do is we can actually represent this entire process using a chemical kinetics. We say A n minus 1 combines with the A and becomes AN. So here I have Kg and Kr. or maybe KD. So, if I look at any cluster of size n, it is formed by a cluster of n minus 1 on one monomer, and that leads to this forward reaction with the growth constant Kg for the forward reaction. And then if you look at the backward reaction, this means that AN cluster, AN basically represents a cluster containing n monomers, okay, and this can dissociate in one single step to give a monomer and a cluster of AN minus 1, okay. So, this pictorial representation of this reaction cascade can be simply mapped into this kind of a reaction scheme, okay. So, now the question is, can we think about writing typically this problem is solved in a deterministic setting. You basically write a law of mass action, write for concentration for each cluster size, and then you simultaneously solve them. So, there is a nucleation theory, classical nucleation theory, that it does this way, okay. But now what we want to do is to represent this problem from a master equation point of view, because you can see it is a discrete jump process, Markov process, do it, okay. So here you can write the master equation. So, here we are asking what is the probability of finding a cluster of size n, size meaning number of monomers in that cluster being n, okay. So, you will see that this becomes KGC P of n minus 1 minus KR KD n KGC P of n plus KD P of n plus 1. So, this term is the forward reaction, okay, and the forward reaction rate depends on the rate constant Kg. So, here we assume that the monomer is an excess quantity which can be represented by some concentration. So, we do not have to track the concentration of the monomer separately, okay. So, we have C as a concentration of the monomer, and then the state to find the cluster of size n minus 1, that is this probability, okay. So, the forward rate usually you write as Kg times concentration of A, concentration of this, okay. So, here we should be writing probability of A1, but I said that this is a large reservoir, large number of monomers available. So, we treat this as a quasi constant, okay, some concentration. Then what happens is the backward reaction depends on the rate Kd times the concentration, which is actually the probability of finding n, okay, the forward and backward as far as n is concerned. And suppose this two represents that you have a cluster of n, it can take one more monomer, it can become n plus 1. So, that is a destruction, that is a loss quantity, loss term. And then you can have a cluster of n plus 1 and you can dissociate and can create P of n. So, that is just like how we wrote this, look at this diffusion equation, very similar, okay. I am just changing only the prefactors, the constants are different now. And again there is analytical solution for this, but I will not deal that here. I will give only the reference for you to check. So, typically the nucleation, this n can go up to hundreds, okay. So, basically you are going to set up hundreds of equations and then solve them simultaneously using numerical methods. This paper talks about the analytical solution of this problem. I am giving this reference because if you try to solve this numerically and you can benchmark your numerical data, numerical results with these analytical solutions. This is a very simplified model for a bacterial growth, that you have a source, and this source term produces bacteria A at certain rate V, okay, and this bacteria can also die, okay, and that is the for backward rate. Parallelly, once you have a bacteria, it can also divide into more species. So here each bacteria can give rise to 2 bacteria at certain rate K. Okay. Set up the chemical master equation for this scheme of reactions, and they will check your answers. And if you have done this, also do another problem where you have a bimolecular reaction, A plus B going to C with rate constant K1 and K2, where you want to treat number of molecules of A, B, C, all of them as a stochastic variable. Okay, so it's going to be a 3-dimensional problem. You have to track the quantities of all. So your probability distribution function P has to be a function of Na, Nb, and Nc. Okay, so write the chemical master equation for these 2 problems and then show your results. Anyone? You should get something like this, that due to the forward reaction, right? So when the state is n minus 1, the forward rate will make it n minus 1 to n plus 1, n minus 1 to n. So that is plus positive quantity. When the current state is at n, any forward reaction will take it away. So minus V P of n. So this too takes care of the forward reaction. And if you look at the backward reaction, when the state is at n plus 1, a backward reaction can take it to n. So there is a positive quantity. When the state is currently at n, a backward reaction will take it to n minus 1. So loss quantity. So here there is only one forward reaction. N will become n plus 1 because this reaction creates one extra A. If the state is n, it becomes n plus 1. If it is n minus 1, it will become n. This adds 1. Then you can think about 2 situations. One, that is when the current state is n minus 1, a forward reaction whose rate is rate constant times the number of molecules at that point, which is n minus 1. This is a forward reaction leading to the formation of n minus 1 to n. When the current state is at n, it will lead to n plus 1. So that is a loss term, and you have Kn, that is the rate constant times the number of molecules. So, you want to find out the probability of finding Na, Nb, Nc at time t. So, the forward reaction can both create and destroy state n. So, this one is if the state is at n minus 1, Na minus 1, Nb minus 1 and Nc plus 1, one reaction, forward reaction will take it to Na, Nb and Nc, right. Why is that? Because this forward reaction should take you no, this is the forward reaction, right. So, right now I am at Na minus 1, Nb minus 1, Nc plus 1. If the forward reaction happens, oh okay, it should be plus 1, right? No, yeah, it should be plus 1. Yes. Okay, let me just check my notes. Yeah, so this is going to be plus 1, and this is minus 1. Yeah, right. So, that is Na, Nb, Na plus C, okay, and then K2 C plus 1. Yeah, those other terms are correct. So, one problem with this approach you have to remember, if you try to solve this numerically, you got 3 independent variables here, okay. So, for each, suppose if you want to take about hundreds of molecules, you have 100 into 100 into 100, that means number of discretization. It's going to be very expensive to do that, okay. So, maybe you can do it for a very small number, maybe 10, 1 to 10 for each molecule, that will give you about 1000 equations, okay. So, that is why we make an approximation that one of the species is more in concentration, so you do not have to explicitly treat them and reduce into a one dimensional problem. Alright, okay, so we stop here, and I have given references to all this problem, and if you are interested you can go to the original paper and see how they have managed these equations. Typically they look at some analytical problem solution, so if you are curious you can look into it. So, that is it for now.